let me turn to this afternoon's speaker. Chetan Nayak is another longtime participant in the Aspen Center for Physics and an avid hiker and outdoorsman. He comes to Aspen a lot, and he's done things which leave me in awe. He's done the 4-pass loop in a single day. He's climbed Pyramid in the Bells multiple times. But much more importantly, he's one of the world's great creative minds, a visionary whose understanding of the weird properties of quantum mechanics, which get ever more weird as the more we look into them, has changed the way we think about things. And indeed, his work also has related these weird properties of quantum mechanics to things that can be measured and designed. Chetan got his PhD at Princeton. He worked with Frank Wilczek, who was then at the Institute for Advanced Study. He did a stint as a postdoc at the Institute for Theoretical Physics in Santa Barbara. Then he moved to UCLA, and then continuing with the Santa Barbara, the Southern California theme, he was snapped up by Microsoft Research Station Q, where he's part of a team working to bring quantum weirdness into everyday life through quantum computing, quantum metrology, and beyond. And today, he's going to tell us about a new visionary idea, time crystals in periodic systems. So please join me in welcoming Chetan.
Thank you very much. Thank you for the kind introduction, and thank you all for coming here today. It's really a pleasure to be here. What I'm going to be telling you about is some recent work on understanding some new states of matter and their interesting properties. And by way of introduction, which I think is appropriate for Aspen, I want to start out with the beginning of the 4th movement of Dvorak's New World Symphony, which looks like this. It's 2 notes and a rest, and then 2 notes and a rest. And let's imagine we had an orchestra playing that, but they did something very boring, which is to say they just kept on playing just that. Instead of going into the rest of that movement of the symphony, they just kept on playing those 2 notes and rest over and over and over again. Okay? Which would sound something like this. Okay? Over and over again, like a metronome. Okay? And let's suppose we had many musicians playing this. In fact, many orchestras playing the same thing. They'd all be playing in tune. Well, actually, during the playing of that kind of boring piece, if you were sort of tuned in the middle, you wouldn't know if they were playing the 2 notes. You wouldn't know if they were playing AC, rest, or if they were resting first and then playing the 2 notes, okay, unless you knew exactly when they started. And you could imagine that, if some of the musicians maybe lost their concentration or whatever, they would end up playing the wrong thing, which is to say they might rest first and then play the 2 notes, okay, and end up, being, off, relative to all the other musicians, because they'd be resting when everyone else is playing and playing when everyone else is resting. And if you that's going to sound not like what it's supposed to sound like. If you have some of the musicians playing out of phase with the other musicians, you end up with something, but let's say a minority, you would end up with something like this. Okay? You have most of the people playing this, okay? And if you playing this, then you would end up with, well, you end up with something sounding like the music of Jaws, okay? But that's not really what we're looking for here, okay? And the reason that you hear that is because the sound waves don't really interact very strongly. They basically just add. So if you've got a bunch of musicians playing and some more other musicians playing out of phase, you just hear both of those sounds, okay? Now, in real life, of course, the musicians would see each other and hear each other and realize what was happening would fix that. But let's suppose that they were all inside of boxes. They couldn't see each other. They couldn't hear each other. They wouldn't know that they were somewhere playing out of phase with each other. And then you would just hear what I just played. But on the other hand, if there were some way that the sound waves could interact, okay, then maybe they could self-correct. Now, of course, musicians can correct, but there's a lot of maintenance involved in making a musician able to do that. Musicians generate a lot of entropy, and there's a lot of training, and we have to keep them alive and feed them. But if the sound waves could just interact and self-correct, wouldn't that be great? I mean, then you would end up hearing something like this. Oops. You would end up hearing you would hear those few musicians playing out of phase, and they would get softer and softer, and you would go over to the right thing. Well, wouldn't that be great? Well, actually, it turns out that that isn't such a crazy thing, because things like this happen in nature. Magnets, for instance, have this self-correcting feature. Here's a block of iron. And in this iron's magnetic because it's got little microscopic magnets inside of it. These are the electrons, and there's spins, which you should think of as small microscopic magnets inside the iron. Well, there's an imbalance between those pointing up and those pointing down. Now, there's fluctuations all the time, and those fluctations, sometimes the spin flips, because after all, this isn't at zero temperature. And those fluctuations are a lot like, actually, when some of those musicians are playing out of phase. Okay? You get some fluctuations, you get some errors, if you will. But actually, the magnet self-corrects, okay? And it actually maintains approximately the right imbalance between the up and down spins. Crystals also have this kind of feature. So here's a regular table salt. You've got sodium and chlorine, and they form a regular pattern. And there's a preferred distance between the different sodium atoms. But there's always some fluctuations. I mean, these things are bouncing around a little bit, and they aren't sitting at any given instant right on those lattice sites. However, they bounce around and fluctuate, and if you look at them on average, they actually self-correct, and the distance between sodium atoms stays the same, including sodium atoms that are very far apart. Okay? These are both examples of what physicists call spontaneously broken symmetries. Okay? Ferromagnets and crystalline solids are two examples. Okay? Superfluid helium, it turns out, is another example. In these cases, and all of these are examples of situations in which the ground state or low temperature state of the system is less symmetrical than the system itself, or meaning less symmetrical than the equations that describe that system. For instance, in our magnet, there really is no preference for up or down. They're both equally good. But once one is chosen, there's actually an energy penalty to reverse spins. There'll be a domain wall between the reverse spins and their neighbors. And that energy penalty favors fixing the errors that occur. Okay? I'll give you another example, okay, which is actually more similar to the main topic of today's talk. So here's the surface of graphene, okay, which if you were to exfoliate it, you would have just a single, this is the surface of graphite, which if you were to exfoliate it, would be a single graphene layer, okay. It's a honeycomb lattice of carbon atoms. And here's a methane gas atom, okay. Well, one thing that can happen is that methane gas can get absorbed on the graphite. And if the surface is exposed to a gas at the right density, then actually it can absorb many methane atoms. Now, if the density is right, they'll end up occupying alternate sites on this honeycomb, okay, which are all the ones in red. That's where the methane gas atoms have been absorbed. Now, you'll see there was an arbitrary choice here of which half of the sites. Okay, it's kind of a checkerboard pattern, but a checkerboard on a honeycomb lattice rather than on a square lattice. And both choices are equally good. Okay, it was a spontaneous choice. Okay, and if all of them had shifted over by one lattice spacing to the other sublattice, that would be an equally good choice. But if part of the system chooses one sublattice and part chooses the other, then there's a domain wall here separating those two choices. That has an energy cost, and that actually suppresses those reverse regions. And so as a result, although one sublattice is just as good as the other sublattice, once the system chooses one of those two, it prefers to stay on that sublattice. Okay? This is the manner in which spontaneously broken symmetries lead to a form of rigidity, which is to say the system wants to choose the same thing everywhere. And that's really the self-correcting feature that I was hinting at earlier with the music that I played for you. Now, as I mentioned, there are always fluctuations. Okay? So even if, once the system has chosen this preferred sublattice, there'll always be some fluctuations. But at any given moment, some region might get misaligned with the rest of the lattice, and there'll be some energy penalty associated with it. But as it fluctuates around, it'll bounce around, and on average, it'll all stay on that sublattice. Okay? But if we heat the system up enough, and you have enough fluctuations, then you can end up in a liquid state where really this crystal on top of the surface has melted. But in that liquid state, small regions will momentarily look crystalline. So if you look at this region here inside the dashed line, it's misaligned, and you look far away, you'll see that this is not even sitting on the same sublattice as this one. But if I look just at this small region, it would look like a crystal. Okay? But if I look over long enough times, okay, what will happen is, on average, that'll all wash out, and the probability, what I'm trying to depict with the kind of transparent methane atoms here is that if I look at any site, the probability of seeing the methane there is a half, okay? And that's a liquid state, okay? But if I were to take any snapshot, as I showed here, you might, in any snapshot in any small region, see something that looks crystalline, okay? And that probably won't be surprising to any those of you who either accidentally or on purpose have done a belly flop into a swimming pool. It's kind of painful. The swimming pool feels pretty solid, right? And here's another demonstration of that it's actually quite subtle to distinguish a liquid from a solid. Here's a swimming pool that's been filled with custard, okay, so mostly water and cornstarch, and you can see that it's liquid, okay? But if you just probe it on very short times, it actually feels very solid. And you can see he's going to walk on it, and he doesn't sink. Okay? Because on very short times, it seems awfully solid, okay? Just as the belly flopper into the swimming pool. But once he stands still and stops moving, and you look at it over longer time scales, guess what happens? He starts to sink in, okay? And over longer time scales, you can tell it's liquid. Now, actually, they had a lot of trouble getting him out of there, because at first they tried to pull quickly, and as I said, on short time scales, it's pretty solid, so if you try to pull him out quickly, it's just going to hold him in like he's fixed in concrete. So they actually had to pull him very slowly out, and if you do it slowly, it's a liquid, okay? So it is actually a subtle distinction between a liquid and a solid, and on short enough time scales, something that acts very much like a solid may actually be liquid, okay? And only by looking over long enough times can you really tell the difference, okay? But as a matter of principle, there's a very clear difference between them, as demonstrated with the honeycomb lattice, which is that either you have equal probability to be on all sites or you don't, okay? So, our self-correcting sound wave oscillation, if such a thing could truly exist, well, that would have to be like methane on graphene, in the sense that, okay, our, self-correcting thing, where the people who are playing out of, with the wrong rhythm, kind of their sound got fixed, and you headed over to the right thing. Well, that would be like something like this, okay, where the methane's absorbing is sitting on half the sites, and well, you could get some misaligned region, just like the people who are playing wrong, but then the whole system would self-correct. Now, what we were calling wrong, of course, that was a little bit arbitrary, because if you're kind of listening in the middle of this, you really can't tell, unless you know right where you're starting, you can't tell the difference, and that's like the other choice. They're really both equally good as long as everyone's playing the same, okay? But once most of the people have chosen one, you really want to self-correct and everyone else to play the same way. On the other hand, if you sort of have 50-50, then you end up with something like this instead, which is analogous to the liquid state, which is the thing that sounded like the shark was getting really close to us, right? So that's the analogy I'd like you to keep in mind, okay? But you should also distrust it a little bit, because that analogy is assuming that time and space are really very similar, okay? Because, this periodic oscillation, which is what this music is, well, that's an oscillation in time, whereas the periodic structure here was occurring in space, okay? And there's a question here, is time really like space, okay? Or is it different? Well, Einstein in his theory of relativity unified space and time and told us that actually to understand, for instance, events, trajectories of particles, even the issue of simultaneity, we needed to think about space and time on the same footing and combine them. And even more so in general relativity, for instance, here with black hole formation, time and space get all twisted together. So if it were true that time and space really could be treated on the same footing, then we would have an analogy, which is that just as a crystal is something that breaks a spatial translational symmetry, which means, look, the world doesn't have any specific preferred places, but the crystal arranges itself in a specific pattern, that something called a time crystal would be the analogous thing in time. So just as a crystal has a preferred periodic arrangement in space, you would have a spontaneous oscillation in time. And this is an idea that my former PhD thesis advisor, Frank Wilczek, kind of enunciated crisply a few years ago and asked whether this was possible and suggested that it actually was. Okay? That was controversial at the time and criticized, and many people kind of shot holes in some of those arguments, culminating in work by my friend Masaki Yoshikawa and his junior colleague Haruki Watanabe, who showed, no, time crystals don't exist, okay? That idea doesn't really fly. Time and space aren't really the same. But sometimes in physics, when there's a no-go theorem and you prove that something can't happen, really it should be viewed as a challenge to figure out what the loopholes are in that theorem. And in this case, one of the assumptions was the assumption of thermal equilibrium. Okay? And once you assume thermal equilibrium, it's really kind of anathema to the idea of a time crystal, because equilibrium really is, in some sense, the statement that things aren't really changing, that they're stable in time. Okay? There's a little more to the argument than that, and it's fairly technical, but that's kind of at the heart of it. Now, I think most people, myself included at the time, thought that this was kind of the end of the story, because that's a pretty good assumption, assuming thermal equilibrium. If one departs from thermal equilibrium, well, one can have all kinds of oscillations and all kinds of unusual behavior, but what you wouldn't say is that it's at all analogous to a ferromagnet or a crystal, which are phenomena that occur in thermal equilibrium. And thermal equilibrium carries with it all kinds of good properties that one would want to hold on to if you were trying to draw an analogy. Okay? In particular, for instance, you can have things like this. You can have, in Rayleigh-Bernard flow, one can have periodic oscillatory phenomena. For instance, when you take a pot and you heat it up, you're heating it from the bottom, and then heat is escaping from the top, well, that will set up periodic flows. But this requires an energy flux through the system, only occurs in open systems. It doesn't have this generalized rigidity that is a property that we'd want to have, that crystals have, that ferromagnets have, and so on. Similar things happen with oscillating chemical reactions. May have heard of something called the Joseon effect occurring in superconductors. When one drives a current through the superconductor that's sufficiently large that it generates a DC voltage, you get an oscillating current associated with that, but there's a net DC current flowing through the system in general, heating occurs. So these are all situations in which you're not really in equilibrium and don't have the kind of properties that we'd like to have in thermal equilibrium. And so these are not the kinds of things one would ordinarily call a time crystal. So, Watanabe and Yoshikawa's proof really said, well, yes, there are things like this that can happen, but if you are looking at thermal equilibrium, things that are analogous to spatial crystals, to ferromagnets, to superfluids, and so on, time crystals aren't going to occur. Okay? Now, okay, but that's not really the last word on equilibrium. It turns out that in spite of that, it's a little bit too restrictive, okay, to restrict ourselves to thermal equilibrium in the following way. It turns out that what we now understand is the culmination of some work over the last 10 years, is that there exist non-equilibrium systems that actually have all of the good, quote unquote, good features of thermal equilibrium systems. And the reason that they have those good features, the generalized rigidities and so on, is that the equations describing these non-equilibrium systems can be transformed to look just like thermal equilibrium. Or another way of saying it is that these systems, though outside of equilibrium, actually, if looked at in the right way, really are just as good as thermal equilibrium. Okay? And I like to call these systems crypto-equilibrium, crypto meaning hidden, that these are a hidden equilibrium. They're non-equilibrium systems, but hiding inside them, really, at their heart, they're like equilibrium systems. And it turns out that in crypto-equilibrium, time translational symmetry actually is a symmetry just like any other, and you can have, or you can start to ask more reasonably questions like, do time crystals exist? Okay. And in recent work with my brilliant graduate student Dominic Else and colleague Bela Bauer, what we discovered was that yes, in fact, in crypto equilibrium, time crystals do exist. And what we showed is that in a series of papers, that time really is just like space in these systems, and time translation is just like any other symmetry, and just as crystals break spatial translational symmetry, and ferromagnets break the symmetry between the spins pointing up and down, similarly, time crystals break a time translation symmetry. And so this led to various things in the popular press that captured some of this flavor, but not entirely accurately, but did correctly say, time crystals might exist after all. It's not quite an open and shut case. One of them said, well, Microsoft thinks time crystals may be viable after all, okay, which may have been a backhanded compliment. Motherboard just said, well, what's a time crystal? So, in slightly more colorful language. So what's this all about? Okay. Well, came up with a theoretical model, and Floquet is a technical term, which I'll hint at a little bit later for this type of time crystal. And basically, we start out with a chain of spins, or in other words, little microscopic magnets. Okay. And this model is going to involve some manipulation of this, and we're going to see that it has that self-correcting feature that I mentioned, which makes it analogous to a crystal in a specific way. Okay? And this thing can be manipulated in a couple of ways. The two ways that we're going to take advantage of are we're going to apply a magnetic field that takes these spins and rotates them. Okay? And we're going to rotate them by approximately 180 degrees. Actually, it doesn't have to be exactly 180 degrees. If we rotate them by exactly 180 degrees, and we did it twice, we'd get back to where we started, and that wouldn't be any huge surprise. But if you rotate them by 170 degrees, okay, you'd rotate them twice, and you wouldn't expect to come back to where you started, and you wouldn't in general. Okay? So, but we're going to do this kind of approximate rotation. The other thing we're going to do is we're going to allow these spins to interact with each other ferromagnetically, meaning they want to try to line each other up. And we may or may not apply, in addition, a random magnetic field to these spins pointing in the same direction in which they prefer to lie. Okay? And there's a history of thinking about systems that have been manipulated in this way, periodically driving them using these kinds of these manipulations, going back to some very interesting work that I guess is cut off, unfortunately, by a physicist in Slovenia named Thomas Prozin, who's not well known but has done a number of really impressive things, and down to work by Gil Rafael, who's here at the Aspen Center right now, that really kind of pointed this in the right direction for thinking about time crystals, and then some beautiful work by a group in Dresden and a group in Princeton developing these ideas. And what we're going to do is take these manipulations, okay, and apply them periodically. So for some period of time, t1, we're going to rotate these spins by applying a magnetic field, okay? And again, only approximately 180 degrees, okay? And then in the next sequence, we're going to let them interact and maybe apply a little random field, slightly different field to each spin. And then we're just going to keep doing this again. Go back and do the rotation, do the interaction, and so on, like this. T1, T2, T1, T2, and so on. And the period of this manipulation, the period of this drive, is capital T, which is T1 plus T2. Okay? And the question is, when we do this, what happens? Okay? Well, there are roughly three things that can happen. Okay? The sort of generic, or the thing that I think most people thought was the only thing that would happen, is something that physicists call the eigenstate thermalization hypothesis, which is just a very complicated way of saying, well, it's just going to heat up to infinite temperature. You keep driving it periodically, you're pumping energy into the system. That energy gets thermalized and spread over the degrees of freedom of the system, and it just keeps on heating up. Okay, it doesn't heat up to infinite temperature. Hopefully you realize it's heating up and you stop. Okay, but it heats up as it continually heats up while you drive it. Okay. What we learned in the last 10 years or so, starting with some really beautiful work by colleagues of Andy's at Columbia, Igor Lehner and Boris Altshuler, is that there's another possibility called many-body localization. And in systems that have this property, okay, it never heats up. Okay? In fact, the system, regardless of what initial state you start in, it actually always looks as if it was at 0 temperature. Okay? Now, this requires a lot of impurities, okay, and by impurities, I mean anything kind of random, like the random fields that I was describing earlier. So it's a little bit special in that sense, but nevertheless very interesting as a counterexample to what was the conventional wisdom. And then there's something called pre-thermalization, okay, also relatively recently appreciated. And this is a system that actually does heat up to infinite temperature because of the drive. But if the frequency of the drive is sufficiently high, then it actually heats up very, very slowly. In fact, exponentially slowly. So as a result, because of the exponential slowness, for a very long period of time, the system doesn't heat up to infinite temperature. And in fact, these two cases over here are examples of what I would call crypto-equilibrium. Even though these systems are not in equilibrium, they're being periodically driven, this one, in fact, looks like it's at 0 temperature, which is one extreme case of thermal equilibrium. And this one, it turns out, also looks like, when looked at the right way, over that exponentially long time during which it doesn't heat up, also looks like a system in equilibrium. Now, you may object and say, well, this one is heating up, albeit slowly, but it takes exponentially long time for it to heat up. And as Keynes said, in the long run, we're all dead. So the fact that it eventually heats up maybe isn't something we should worry about too much. Okay? So if we were to take one of these two routes to crypto-equilibrium, that's how we could potentially get a time crystal. Okay? So what happens? So we take our system of little magnets, which is what I'm using to call, which I call spins, and we do a rotation by 170 degrees. Okay? So you can see the magnets of the little spins here have rotated. They haven't rotated by exactly 180 degrees. They've rotated by 170 degrees. Okay? Then you let them interact, and sometimes when they interact, well, that causes nearby spins to kind of tip away from each other. Sometimes those balls will exchange the spins with each other, and so you get some further evolution of this. You then do another 170-degree rotation, which rotates this 170 degrees. It's not getting back to exactly where it started, because after all, they weren't 180-degree rotations, and the spins interacted in some complicated way. You let the spins interact again, and you can see you've ended up with some state like this. And you keep doing this, and what do you expect? Well, you expect to just scramble everything. Okay? And what I mean by these arrows pointing in every direction is that if I look at any of these spins, on average, any one of these spins has equal likelihood of pointing in any direction. Okay? So it doesn't really have any preferred direction. It's more or less, it is actually not more or less, it is forgotten what state I started out in. It's all washed out. And again, this is sort of the standard assumption that we would have made about a system that was being periodically driven like this. Okay? And this is a lot like, well, I'll return to what it's a lot like in a moment. But first, let's ask, is this the only thing? Is this what really happens? Okay? Well, what it's a lot like is it's a lot like a liquid state, okay? Because you've washed out all of the memory of what you start out with. You've manipulated it, done these 170-degree rotations and so on. And by the end of this, it can point with equal likelihood in any direction. And there's no difference between the end of an even period and an odd period, because I go one more period, do one more 170-degree, and one more interaction. And well, they start out, by the time I've gotten to where they have equal likelihood to point in any direction, going through one more cycle doesn't change anything. It's still equally likely to point in any direction. And that's just like this liquid state of methane on graphite. It's the same at even and odd multiples of t here, same probability to be on either lattice site. Okay? So this is really what a liquid state in time would look like, which is, here I'm showing it in the pre-thermal case, which is that you start out with some initial state, and you start out, and it's indeed oscillating as you start out, because you do the 170-degree rotation, you let it interact a little bit, you do another 170-degree rotation, and it's going to bounce around. But after some relatively short time, that all washes out. And the red here is what's happening at the end of an even period, and the gold is what's happening at the end of an odd period. And although they are different initially, they'll wash out, and you'll get this long time over which basically they look the same. Okay? That's like a liquid state. So if we want to think about a time crystal, what we're really thinking about is something that looks like this instead, which is there's some initial transient over which the system forgets some of its initial state, but not all of it. And as you continue into this long time regime, it now oscillates between red and gold, between even and odd cycles. Okay? So that would be a time crystal. Now, how can we get this? Well, if you think about it, what we need is we need those interactions, okay, to be stronger to stabilize this in step 2. Okay. That's how the spins can try to lock together. And in such a case, well, what would happen? We do our 170-degree rotation. Okay. Spins would not flip precisely in the opposite direction. It's only 170-degree rotation. You then interact. That jump scrambles them up a little bit. Okay. You do another 170-degree rotation, and you've not quite reversed them. You let them interact. That scrambles them a little bit. And you can see here, you've ended up not really exactly opposite of where you started, which you shouldn't expect, because after all, it's 170-degree rotations. But then you do this more and more and more. And at the end, or not the end, but at some much later time, once you've done a number of cycles, you may find that it hasn't all just washed out. And it's not forgotten where it started, and it isn't equally likely to point in any direction. Okay? And what happens in that case, which is a time crystal state, is that if I then go one more period, it's actually rotated by exactly 180 degrees relative to where we started. Okay? So it actually has this self-correcting feature. Even though I only did 170-degree rotation, or it could have been 175, or 178, or something like that, because of the interaction step, what happens is that eventually the system locks in, and every even and odd are alternating perfectly. And this is like the crystal state of the methane on graphite. Okay, being opposite at even and odd is like this choice of sublattice. Okay. Now I've drawn here kind of a cartoon limit where the reds are always on one sublattice. Now of course it would still be a crystal state even if it were 75% likely to be here and 25% chance of being here, as long as there's some unbalance between those two. Okay. So even the only situation in which we would really call liquid is when it's 50-50 and equally likely to be on either. And similarly here, the system can forget some of its initial state, but whatever it retains at late times will oscillate exactly by 180 degrees, which is sort of what I was depicting over here. That it does forget some of its initial state, but then there's this long time over which you get perfect oscillation of whatever's remaining. Okay. Okay. So the oscillation self-corrects. Okay. In other words, it really ends up sounding like this. Okay. Where you have some errors occurring here, but in spite of those errors, what happens is that the initial you forget some of the initial state, but then you lock in eventually so that you go an exactly 180 rotation, which is really like saying AC, rest, and so on, rather than the reverse. Okay. So, we cooked up a model that has this property, and then my friend and colleague at Berkeley, Norm Yao, got very excited by this and talked to his friends, Chris Monroe, okay, who is an experimentalist at the University of Maryland, who works with trapped ions, and Misha Lukin at Harvard, and came up with two different experimental realizations of this theoretical idea. Okay. One of them, as I said, involves trapped ions. So here is a trap in which ytterbium ions are trapped in a line. Okay. So this picture is taken with a special kind of optical camera, but it turns out that they actually give off light. And if you look into the trap through one of the windows, remarkably, even though you're looking at a single ytterbium ion, you can actually, with the naked eye, see them. And these ions can be made to rotate by 180 or 170 degrees, or however you like. And they also can be made to interact with each other. Okay? The interactions that we need could be just between neighboring ions, or they could be longer range, and ions could interact with their neighbors and second neighbors and so on. It turns out that when we're making a linear chain of these, it's advantageous to have longer range interactions. And what they found when they modulated the evolution of the ions in the periodic way that I described was that, indeed, when the interactions were off or weak, what they found is that this kind of beating pattern, which means that the system was very sensitive to how much you deviated away from 180 degrees. A way to quantify that is to take its Fourier transform, which is to sort of look at the periods, the frequencies that are inside, and the fact that there's two peaks here which vary depending on how much you deviate from 180 degrees is a sign that the system isn't locking in. Okay? On the other hand, when the interactions are strong, even as you deviate away from 180 degrees, there's just the one oscillation frequency, which is a signal of a time crystal. Okay. The other experimental realization, okay, turns out to be with what are called NV centers in diamond. So these are diamonds that have some flaws in them, okay, so they're not flawless diamonds. And the kind of flaws they have are so diamond is this kind of lattice of carbons, and some of those carbons are missing. Okay, that's the V in NV. It's a vacancy. Another thing that can happen is that the carbon could be replaced by nitrogen. And when you have a situation where there's a nitrogen in place of a substitution for carbon sitting next to a vacancy, okay, well, in that case, it turns out that that effectively acts like one of these spins that I was talking about, just like in the ion case. Okay. These have been of great interest recently because the spins associated with NV centers in diamond can be manipulated and imaged and so on in many beautiful ways. What Misha Lukin and his group took was one of these diamonds that has many of these, a very high density of these flaws, often called black diamond because it actually looks black. It's a different kind of black diamond than we're used to talking about in Aspen. Subjected it to a periodic protocol in which they pulsed it in the ways we just discussed, doing these rotations that were, in some cases, 180 degrees, in some cases deviating away from 180 degrees. And as a result, and then allowed these, or actually induced interactions between them. And what they saw was very similar to what was seen in the ions. Totally different system, okay? Totally different system. But what they saw was very similar, which is to say that when the interactions weren't sufficiently strong, you didn't get any locking in, and you see these two peaks in the Fourier transform, which are a signal of the fact that it's not really perfectly locking in and oscillating. And conversely, when the interactions are strong enough, what they saw was that everything locks in. Okay. Now, on the other hand, what you'll notice in this plot, as in the plot that I showed you earlier, was actually that although there is indeed this oscillation, you can make out it's actually getting weaker as it goes on, which is not what we'd expect, naively at least, from a time crystal. So there are things about these experiments that we don't understand. I think in the case of the ions, the reason for this has to do with the fact that it was not a very large system of ions initially, and in the next generation of experiments, they are looking at larger systems, and what appears to be the case is as you make it longer, this decay goes away. Okay? In the diamond NV centers, it turns out there is probably more complicated physics going on in here that's not in the model that we don't understand yet. Okay? So indeed, I think these experiments really are consistent with the story about time crystals, and I think one might even say, yes, time crystals exist, but lots of characterization does still need to be done, okay? Because although they broadly agree with what's predicted, there are some things we don't understand, and I think there's more characterization. There's some interesting ideas floating around about how time crystals might be used for metrology, okay? The idea being, look, if you want to measure lengths, you wouldn't use a liquid to measure lengths. You would use a ruler that's a solid, okay? And similarly, if you want to measure times, or in some cases time differences, you simply want to use something that locks in at a certain frequency or certain time period, as time crystals do. And it turns out that time crystals, in some sense, are the tip of the iceberg. There are many other states that can occur in crypto-equilibrium that realize even more exotic states of matter, some of which have analogs in actual honest-to-goodness equilibrium systems, some of which have no such analogs and involve things like topological phases of matter and things that perhaps even are interesting and useful for quantum computation. So I hope that over the course of this lecture I've been able to introduce you to something that to me is very new and exciting in terms of understanding and manipulating states of matter, which even just a few years ago we all presumed did not exist. So thank you very much for your attention. I'd be glad to answer your questions.
Okay, thank you. So the floor is open for questions. Sir.
Mode-locked lasers are used for metrology. I'm discussing mode-locked lasers that are not driven by an AM or FM source.
Yeah.
Is a mode-locked laser a time crystal, or what are the differences?
Yeah, no, that's a great question. And actually, in fact, often when I've given talks on this topic to physicists, the most common type of question I get is X a time crystal? Where X could be a laser, X could be spontaneous parametric down conversion, it could be the AC-Josephson effect, it could be those Rayleigh-Bernard flows that I talked about. So that is really an excellent question and kind of one of the first questions that I think comes to mind. I think the answer to that is no. And I think the reason is that all of those systems that I just rattled off are systems that do not look like equilibrium systems in any sense. They don't possess the properties of equilibrium systems. And in reality, all those systems would really have fluctuations, and those fluctuations would eventually cause their phase to wander. It may be that the fluctuations are really small, and so over any reasonable period of time that we want to apply it to, phase wouldn't wander. But it would actually wander. But they often have stabilization mechanisms that usually involve the system being open. And that is an interesting and different phenomenon. But I wouldn't call it a time crystal. And I think when you have an open system, lots of interesting things can happen that are not, such as in an open system, well, the entropy can decrease. Why can the entropy decrease? Well, you actually increase the entropy and throw the extra entropy out the window, and it looks like in your system all that extra entropy has, is gone away. And you can have in open systems, if you have some fluctuation that's inconvenient, well, you can throw it out the window, okay? Because you have an open system, you have a big reservoir, a big bath. And there are states of matter that rely on the openness and the fact that you can sort of expel unwanted fluctuations and lock in the behavior you want. They don't behave like equilibrium systems. Not to say they're not interesting and useful, but they're not really analogous to time crystals.
the more energy you add to it, the slower it would react, which would be exactly like that Newtonian fluid when he was able to create a solid versus a liquid.
Let me.
Actually, it was the
Yes.
pre-thermalization.
Yep.
Yeah.
Okay.
So
Okay.
the more energy you put in, the more solid it becomes, and the slower the reaction would be.
No. Yeah. So let me explain it again. So pre-thermalization occurs in periodically driven systems when the drive frequency is very fast. So remember, in the particular case we're talking about, you rotate it with the field, you let it interact, rotate with the field, let it interact, and so on. And basically, there's some period for that periodic driving. If you make that period very short, so you do everything very fast, then actually, if you think about it, if you're doing oscillating very fast, if you look at it from a distance, you can't actually, if you have a slow oscillation like this, it's kind of easy to tell that it's oscillating. If you have a really fast oscillation like this, from a distance, it actually might just look like a straight line because the oscillation is so fast. And indeed, that's what happens in the high frequency limit, because the oscillation is so fast in the drive, it actually it looks to a very good approximation like a system that's actually static. It's not being driven at all. Now, of course, it isn't static. There really is, if you look at it closely enough, an oscillation. But the interesting thing is that actually only shows up at exponentially late times. You might have naively thought, well, okay, I just kind of step back, and when the time is sort of comparable, to maybe the amplitude or something like that, I'll notice that there's actually an oscillation, but it's not. It's an exponentially long time, and so that very quickly can get much longer than the lifetime of any experiment or observation, and so it's not. It's really not analogous to the guy who was walking on the custard. It's a different thing. Yeah.
So it's not a Newtonian fluid.
No, that was a non-Newtonian fluid, that guy walking on the custard, certainly, but this effect is not really analogous to that.
Okay, other questions? I see stunned silence. Sir.
Have these ideas been explored for quasi-periodic crystals as opposed to periodic?
There are some papers that talk about that, time quasi-crystals and so on. I would say that, just no experiments yet. There have been some theory papers, and I would say they're not, to me, that convincing. So I think there is something still to be worked out there. Yes.
So, were you pointing me out?
I'm sorry, you in the black shirt. Then we'll get to you in the blue shirt.
Time
Oh, well.
crystals be used to improve quantum-based computers?
Okay, it's a good question. So the answer is, of course, I don't know, but I will. I'm going to speculate here. Okay, which is, as I mentioned, these are examples of states of matter that don't occur, in equilibrium, and for certain types of quantum computers, you want to exploit novel states of matter that have some kind of rigidity associated with them, some kind of self-locking features that let you get certain quantum gates, okay, very accurately. And it turns out that many of these ideas carry over, as I was mentioning. I mean, unfortunately, it's a little bit of just a buzzword, but I'll say it, topological states of matter, which could be very useful for quantum computing. It turns out that in the periodically driven context, you have analogous to time crystals, topological states of matter that don't occur in equilibrium and may allow you to have some kind of locked-in gates that you couldn't otherwise get. Okay.
So if I may add, there is a famous story I can't resist telling, that back in 1830, when Michael Faraday was doing the first experiments that led to our modern understanding of electricity and magnetism, his laboratory was visited by William Ewart Gladstone, who was the British Prime Minister, and Faraday showed him the various experiments, and Gladstone said to him, in essence, "Sir, what good is this?" And Faraday looked at him for a moment and said, "Someday, sir, you will tax it." And this is an analogous case. Now, you had a question.
Sorry, yeah, trying to remember. Okay, so what I noticed is when you compare them to regular crystals, regular crystals do seem very stable throughout time. They don't change a whole lot without outside influence, but the time crystals you were describing require a constant human or machine or something else
That's right.
using energy to keep it going. Are there any that can just fluctuate on their own?
Good question. Yeah. So let me though draw. Oh wait, maybe hang on. So what you said is absolutely true, but I just want to kind of draw this analogy a little bit, which is in this particular type of crystal I was mentioning here, where you have the methane adsorbed on graphite, there was already waiting for the methane this periodic structure of the graphite. Now the methane still had a choice here, which is it could choose to sit here or sit here, okay, which it spontaneously did, but there was some intervention, human or otherwise, that laid down this honeycomb lattice on which the methane could play out its spontaneous choice of which sublattice to sit on. So in our time crystals, our periodic drive in time is analogous to this periodic structure that was laid down in space for the methane. Okay, so does that make sense? And I'm going to get to the second part of your question in a moment, but before I do, does that make sense?
Yeah, so
Yeah,
you're
okay.
laying out the lattice and it's just fitting into its form.
Yeah, exactly. So what we're doing is we're laying out the lattice, and it turns out that it adopts a periodicity it's a lattice in time, and it adopts a periodicity that's different from the underlying periodicity lattice by a factor of 2 in this case, but it could be 3 or it could be anything. Okay? Just like here, the methane has chosen an underlying periodicity that's different from the periodicity of the graphite. In this case, because the density is half, it's only on every other carbon atom. But if the density were different, it could have only been every third or something like that. Okay? Now, that still leaves open the question you asked, which is if I had an undriven system, could such a thing occur? And so the answer is, I think the only case that I really believe this can happen is it turns out there is an analog of pre-thermalization that occurs in undriven systems also, okay? And it requires some special, I mean, there are some special features associated with it, but there are I believe that such a thing could occur. And there were actually experiments back in the 80s that were, NMR, that were looking at nuclear spins that may very well have, they didn't use the word time crystals in those days, but may very well have inadvertently chanced upon something that was rather like a time crystal. Now, so the answer is, I think it can exist. I think it's a little less generic because in undriven systems, pre-thermalization requires some extra, I don't want to call it fine-tuning, but it does require a little extra work to get into it because pre-thermalization is a little more easily spoiled in undriven systems for reasons that I can explain in more detail, but it's a digression. So I think there is an undriven version of this story, but it's sort of a little more special, a little less generic. Okay.
All right, so it's coming up on 6:30. I'll ask, is there one more question? All right, well, I'm sorry, Chandra, I didn't see you.
Yeah.
In space, one has the sense of both backward and forward. One can go x and minus x. In these systems, can you speak in any way of going backward in time? Because it's periodic.
I don't know what it even means to go backward in time. So
I'm sort of trying to ask, is the answer to the question this gentleman asked related to the fact that time and space are not the same things? Time, in some sense, always goes forward.
Well, I agree. Time and space are certainly not the same thing. There is, look, there's a causal direction here, right? We believe that there's causality. I guess what I'm saying is that in some respects, time and space are actually the same, and the fact that these symmetries can be spontaneously broken, and more, there's actually quite a bit more structure underlying this in which time and space act the same, even though they're not really the same.
All right, well, I think on that note, since time is going forward, let's thank Chetan.
Okay, thank you.